We can use KSP, that solubility product constant, to determine what's called the molar solubility. We've talked about molar volume and molar mass. Molar solubility is the amount of, or the number of moles of a compound that will dissolve in 1 liter of solvent. So, if you had a liter of water, how much sodium chloride would dissolve? That's the molar solubility. So if we look at this silver chloride, when silver chloride dissolves, which it doesn't do very much, it will separate into its ions, silver ion and chloride ion. The equilibrium constant, the solubility product constant for this is 1.77 times 10 to the minus 10. So K is a very small number. Does this favor the reactants or the products? It favors the reactants. When K is a small number, it means that the reaction stays mostly as reactants. It goes very little to the right. So molar solubility is often abbreviated with a capital S. That's the moles that will dissolve in 1 liter of solution. So how would we do something like this? Well, what would be the expression that we would use for KSP for this compound? It's the products over the reactant. Well, the reactant's a solid, right? So that doesn't come into the equation. And so KSP equals the silver ion concentration times the chloride ion concentration. And we know what it is because it was given to us in the problem, 1.77 times 10 to the minus 10. The stylus doesn't write as well when there's all sorts of child finger smudges all over the screen. But I just have to check my game. I'm playing Clash of Clans or something silly. So this is all very nice, right? But what we want to know is how many moles of silver chloride would dissolve in 1 liter of solution. Here we have 2 concentrations, and they don't give us what those are. Where did the silver ion come from? From the silver chloride, right? And the chloride also came from here. So what do we know about the relationship between silver ion and chloride ion concentration? They're the same, right? Because for every 1 mole of silver ion, we get 1 mole of chloride ion. So that's kind of a stoichiometry idea. There's 1 mole of silver ion to 1 mole of chloride ion to 1 mole of silver chloride, right? Those are mole ratios that we learned how to figure out. It's from the coefficients. So that tells us that the concentration of silver ion is equal to the concentration of chloride ion. Oops, that's not what I wanted to do. These are equal. Because it's like taking apart a pair of shoes. There's 1 left shoe and 1 right shoe. And if all the shoes came in pairs, then you have an equal number of left and right shoes. There's no way to get an uneven number. They're going to be equal. So this equals that. We could call that X if we wanted to. Or we could call it S. Because this is moles per liter. And for every 1 mole of silver that dissolves, we get 1 mole of chloride and 1 mole of silver. So S times S, we normally call that S squared, right? S squared equals 1.77 times 10 to the minus 10. How do we find out what S is? square root. So S equals the square root of 1.77 times, 10 to the minus 10. So square root of 1.77 times 10 to the minus 10. 1.33 times 10 to the minus 5. That has units of moles per liter. Because just by convention, when we calculate these constants, all of the concentrations are in moles of that substance per liter. So this is moles per liter, that's moles per liter. We leave the units off of the constant though. So this is our answer right here. Any questions? Does that make sense at all? Kind of? Let's do another one. Calculate the molar solubility of calcium sulfate. This problem has no numbers in it. We're going to need the chart. Let's go back to the chart. Solubility product constants are listed in tables. There's an interesting reference book called the CRC Handbook of Chemistry and Physics, and it's like 4 or 5 inches thick, and it's just packed full of numbers. And things like solubility product constants for pretty much anything you can imagine are listed in there. So, now in the age of the internet, we don't actually have to carry that around. We can just Google stuff on our phones, right? But we're going to need the solubility product constant for calcium sulfate in order to do this. So there it is, 7.10 times 10 to the minus 5. On an exam, you would either be given the table or in the problem it would tell you what KSP is. This is not something you need to memorize. 7.1 times 10 to the minus 5. Because I have a hard time remembering it just going to the next slide, right? 7.1 times 10 to the minus 5. So we looked up KSP for this compound, 1.70 times 10 to the minus 5. Now what we need to do is we need to write the equilibrium expression here showing how calcium sulfate dissolves and forms ions. Oops, that's a solid. And that will be in equilibrium with its 2 ions. What's the charge on calcium ion? 2 plus. We know that because calcium is in group 2 in the periodic table. And so we should remember that sulfate is minus 2, but if we don't, we could figure it out from the calcium. So there's our expression, our chemical equation. And then we look at, well, what does KSP equal? It's the products over the reactant. Here the coefficients are 1, so we don't need to worry about the exponents. So that's the concentration of calcium ion times the concentration of sulfate ion. Calcium sulfate, the solid, is left out because solid concentrations can't change. And so we decided collectively to leave them out. Then we look at this and we recognize that you get 1 calcium ion and 1 sulfate ion for every 1 calcium sulfate unit that dissolves. The calcium ion concentration will be equal to the sulfate ion concentration. And those will both be equal to the number of moles of this per liter that dissolve. So the calcium ion concentration equals the sulfate ion concentration. We call that S. And that equals the moles of that substance that dissolve per liter of solution. So then we can say that that KSP equals S squared. We know the value for that. So we end up with S being equal to the square root of the KSP. Square root of 1.7 times 10 to the minus 5 is 4.12 times 10 to the minus third. Now we need to put units back on there. That's moles per liter. Any questions? That's what I call stunned silence.